shortly. Question one: a certain amount, that is example, a certain amount of gas occupies 5.0 dm³ at 2 atm and 10 degrees Celsius and 10 degrees Celsius. Calculate the number of moles present, taking R to be what? To be 0.082 atm dm³ per Kelvin per what? Per mole. Alright, so we'll be solving this question last because of space. Alright, so we'll look at the second example is what? Is at what conditions do real gases behave most like ideal gas? You see that now. So at what conditions do real gases behave most like ideal gases? So just drop the answer in the comment section. So I said earlier that ideal gas behave real gas behave mostly like ideal gas at what? At low pressure and what? High temperature. Do you understand? But they deviate from ideal gas at high pressure, which is the one I wrote first in the previously. They deviate at high pressure, low temperature. But when they behave mostly is what? Is low pressure. Are we together? High temperature. When you want to remember easily, just write PT. PT for deviation. This one is high. Do you understand? This one is what? Low. For deviation. But for close, that is when they behave mostly, is when the pressure is what? Pressure is low and temperature is what? Temperature is high. Do you get it now? So don't miss. You need to understand the question first. You need to understand if they behave most like, is different from deviate. Do you understand? Behaving like is different from deviating. If it is behaving, it's just like it wants to assume the state of the ideal gas. If it is like that, they are behaving like. Is that clear? They are behaving like. And if they behave like, that means that it is when their state is what? Low pressure and high temperature. But when they deviate, when they want to deviate, they want to behave differently. That means it will be what? High pressure and low temperature. Alright, so look at the third question. It said, why do real gases deviate at, do you see that now? At high pressure. So they deviate at high pressure, they deviate at high pressure. And here the pressure, they behave like, you see that now. So when they behave like, it is at low pressure. But when they deviate, is what? At high pressure. Do you see that now? So now the question now says, why do real gases deviate at high pressure? Now, one thing is that, let me explain this. Let me explain it like this. Now, let's say that this is a pot. This is a pot, and the volume is here. That is the cover. Your cover of your pot is here. And let's assume that there are gas here. There are gas here like this. Are we together? These are the gases. They will be moving around about, right? They will be moving about. So the volume is a bit wider. So this place can contain them. Though they might collide even with themselves and the word of their container. They will move freely at a point randomly, and they will be colliding and then do all of that. Now let's assume that you now put, let's say, a stone or a big load is what? Is now dropped on the surface of the pot. Is now dropped on the surface of the pot. What will happen to this cover here? What will happen to this cover here? It will what? It will press down. It will shift down. And if it shifts down, you might have it to be what? To be like this here. To be here. Did you see? Because of the pressure. Because of the pressure that is exerted, you will push the cover down. It will push the cover down. Are we together? It will push the cover down here. Okay, from here, you are pushing it, it will push it down here. So we now have something like this is the new cover here now. Do you understand? It was here before. Do you understand? But immediately you drop the pressure, the big stone, it will push it down. Now, what will happen to the gas? The gas will be more compressed, isn't it? They will be more compressed. They will be more compact. They will be more compressed. Unlike when the volume was still large, is that clear? They will be more compressed. And when they compress, the intermolecular force will be observed there. It will be significant. That is why they deviate at what? At high pressure. Because when the pressure is exerted on them, the intermolecular force will be what? Will be significant. Though it might not be as high. That is why they behave. That is why we say deviate, behave. They don't do exactly, but they behave like, or they deviate from. Do you understand? So at high pressure, real gases deviate from what? From ideal gas, because when the pressure is high, the intermolecular force between the gas molecules, it will be what? Significant. That is, it will be noted. It will be what? It will be noted. You understand now? The intermolecular force, the force of attraction, the force of repulsion, it will be what? Significance. They will collide with themselves more. Do you understand? They will collide with themselves more. And of course, it will increase the average kinetic energy. Alright, so that is that. So now let's solve the question one now. Let's solve question one. Let's solve question one. Now we said a certain amount of gas occupies 5. So these are parameters. We have what? 5. So that is in dmq. So it is our what? Is our volume. So V, our volume, equals to what? 5.0 dmq. Our volume can be in cmq. It can also be in dmq. All right. So at 2 atm. So 2 atm means what? It represents which parameter is our pressure at 2 atm, and T, temperature here is 10, right? So temperature is what? 10 degrees Celsius. But we are not going to leave this, we are not going to use this temperature here at 10 degrees Celsius, because the temperature unit should, of course, we can have it in degrees Celsius, we can have it in Kelvin, and we can also have it in Fahrenheit. So, but in calculations, it is usually being advised that we convert it from degrees Celsius to what? To Kelvin. All right, because we have standard temperature and pressure. Yes, standard temperature and pressure. All right, so we convert it to Kelvin by adding what? By adding, that is 10 plus what? 273. Are we together? To give us what? 270. So it will be 283 Kelvin. This is the value of the temperature we'll be using. All right. So they now said calculate the number of moles. You see that now our n is unknown. That's what we are looking for. The number of mole. So let me clean this now and put it here. Equals to 283 Kelvin. Calculate the number of moles present where our R is a constant. I told us it's a constant 0.082 atm no dnq then per Kelvin per mole. Yes. So now from our ideal gas equation, we have it to be PV equals to what? nRT, right? But we are working with what? With N. That is what we are asked to calculate. Calculate the number of moles. So we make N the subject of the formula here. R divided by RT divided by what? RT. R cancel this. So we have N equals to what? PV over what? Over RT. So let's input our parameters now. P is what? 2 atm multiplied by what is our V? 5.0 divided by what is our R? 0.082 multiplied by what is our, let me write it well, 0. So what is our T? Our temperature is 283. So this is that is 0.82, no, 0.082 multiplied by 283. So we have n equals to, that is 10 over 23.206. 23.206. That is n equals to, that is 10 raised to 2.3. But let's confirm. Divided 10 divided by 23.206. Okay, so we have n, which is 0.4309 mole, because we are dealing with what? Number of mole. So this is our final answer. All right, so let's, the one for you to try, you should try this. 2.0 moles of an ideal gas are at a temperature of minus 13 degrees Celsius and a pressure of 280 N. What volume in dm cube, so you are expected to put your answer in dm cube, will the gas occupy at that temperature? So you take your R, which is a constant, to be what? To be 0.0828 em and all of that. So try this and put the answer in the comment section. So thank you so much. Thank you for following to this point. I need you to subscribe to this YouTube channel, turn on the notification bell, comment, okay, this video is nice, you understood this and none of that. So comment and also share to your friends. Share to your friends. All right, see you in the next